just a quick note about that. This is going to be recorded. Okay, go ahead, guys. Okay, perfect. So our project was on different. Okay, I'm Greta.
I'm Owen.
I'm Ellie.
And I'm Kelly.
And our project was on different methods of food preservation that we tested on apples and bananas. Can you go to the next slide?
So I'm doing the Zoom extra credit because I need it. I'm in this classroom, nice as shit. I talk stuff. I'm watching.
Okay.
Lab meeting.
So
This is
some background on
school, just meetings.
topic. The UN Development System.
Yeah. And this speaking of stuff.
The second one, Zero Hunger, which means.
No, my internet is nice. I need to look. Yeah.
Someone is not on mute. A heads up.
You can't. No, watch. Look, I got nice internet, bro.
Can I do it somehow?
Look.
Okay, sorry. So the Sustainable Development Goal we chose was the second one, Zero Hunger, which means everyone has access to
an anomaly. What can I say? This is
the year 2030. And currently, we're not on track to reach that goal, as in 2015, increase the rate of malnutrition. And currently, it's estimated that 690 million people are malnourished worldwide, which is almost.
Honestly, I'm just going to take a picture of each slide.
And that.
So.
Happens, sorry. Sorry, friends on Zoom, if you could please mute yourself, that would be very, very appreciated because we cannot hear very well. Give me 1 second. Apologies. Let me just make sure I get everybody here. Oh, they're all muted. We're all good now. I think we figured it out. Our internet connection's unstable. We're basically we're getting the internet technology today. That's all right. Okay, and this rate is high because of different conflicts like war zones, and climate change has been making it hard for produce to grow, as well as other conflicts like the current pandemic is making it hard for people to have access to nutritious food. So our goal for this project was to find different, affordable, and accessible food preservation methods that will increase the shelf life of produce.
So have you ever tried putting lemon juice on your apples to make them last longer? Well, this works because lemon juice is very acidic with a pH of about 2, and therefore it creates a barrier around the fruit that will react with the atmosphere before the fruit actually reacts with the atmosphere. And therefore, until all of the lemon juice has evaporated, your apple won't go bad and it will stay edible for a longer period. Having done this ourselves, we wanted to test out different methods of food preservation to see if they would be just as successful or more successful than lemon juice. And so we tested these methods on apples and bananas. First, we tried pickling, in which we used a vinegar and water solution. Next, we tried canning, in which we created a vacuum seal to prevent exposure to the atmosphere. We used vegetable oil, which is a non-aqueous substance, to see how this would affect food preservation. We used sugar, which is a neutral solution, again, to see how this may affect the fruit. And finally, we used pineapple juice, which is another acidic solution like lemon juice, with a pH of about 3 or 4, to see if this would work in preserving the fruit for longer. So now I want to ask you guys, which method do you think will be the most effective? And people on Zoom, I can't see you, so if you just want to make note of which one you might think would be the most effective, that's great too. So how many people think pickling? No one? One. Okay, how about canning? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that a hand? Okay. Vegetable oil, 1. Sugar, 0. Okay. And how about pineapple juice? 3. Okay.
Okay, so what's the science behind all of this? So first, what we looked at was kind of based off of our experience and like what people know, just like not naturally, but just like kind of just throughout life experience. When there's more oxygen, food is more likely to rot. Kind of like when you bite into an apple and leave it out, it's going to turn brown. Less water, dehydration, it tends to not rot, which is why you see dried banana chips and stuff like that. Adding heat, it's most likely, we're not adding heat, but more like taking away heat, it's not going to rot, kind of like putting it in the fridge. So adding heat will cause it to rot. And lower pH will cause it to not rot, as we were talking about the lemon juice from, and putting lemon juice on apples. So what we got from the science of all this, we did a little bit of research, and food actually goes bad due to decomposition, and decomposition only occurs because of bacteria and fungi. This bacteria and fungi can only survive when water and oxygen is present and between a certain temperature of 40 degrees to 140 degrees Fahrenheit. While raising the temperature will actually kill everything, lowering the temperature will only slow bacteria growth, which is why when you put things in the fridge, you will see that it will still eventually go bad. And then high sugar, salt, and lowering pH will create a hostile environment for the bacteria. As we see with lemon juice and all that, it'll cause it'll react more with the lemon juice on the outside because there's a lower pH. So what's the real chemistry equation with it? So the main one that we chose to focus on was cellular respiration / decomposition of glucose. So when oxygen is added to the glucose of the apples and bananas, it'll cause it to break down. And this will cause the creation of water, which will allow more fungi and bacteria to grow as it needs water to grow. And it'll also cause the creation of ATP, which is energy, and usually that's in the form of heat, which will then cause it to be a more suitable environment for the bacteria to grow as it's warmer, but not warm enough to actually kill it off.
So polyphenol oxidase is the enzyme that's actually found in fruit that reacts with oxygen to cause the browning. And so this enzyme oxidizes phenolic compounds that are found in the fruit. And these compounds are just a branch of organic molecules. And so then these oxidized compounds react with amino acids and proteins that actually causes the color change from colorless to brown. And so I provided a picture of the reaction below between the enzyme and oxygen that you can see there.
Okay, so then for our reasoning and our hypothesis, there are two primary things we were focused on, and those were the acidity and then the decomposition caused by exposure to O2 gas. So our goal was essentially to limit this to prevent the ultimate rotting of the apples and bananas. So for pickling and canning, by definition, this was literally creating that airtight seal that would hopefully keep oxygen out of the container. And then sugar was a neutral solution, which we wanted to test to see how that would do with the 14 days that we left our solutions. Pineapple juice, again, as Kelly mentioned, was something acidic, so we wanted to see how that would have a role in this. And then for vegetable oil, that non-aqueous solution, we wanted to see how this kind of liquid would keep oxygen out and preserve the food. Ultimately, our hypothesis was that the more acidic the solution was, the better it would be at preserving the food. So we really expected that pineapple juice would be the best method for preservation. So for our preparation, we took a group field trip to the grocery store, and then also another group field trip to the Commons Communal Kitchen. And we were ultimately able to cut the apples and the bananas into 6 equal slices of relatively the same mass and the same surface area so that they'd have the same effect with the solutions. And then for the canning, we used the water bath method. For pickling, we created that 1-to-1 solution of water to vinegar and then sealed that container as well. For vegetable oil and for pineapple juice, we literally just submerged the apples and the bananas in their respective containers in the liquid. And then for the sugar solution, we made a solution of 2-to-1 ratio of water to sugar and then sealed that container. It's also important to note that we did allow exposure to O2 gas by literally cutting into the container with the exception of pickling and canning, where that seal is in the definition.
So our results, we did our results based off a ranking system from 0 to 10, where 0 is a totally decomposed fruit and 10 is a perfect fruit. And it was based off of factors such as molding, browning, and dryness. And as you can see here, the best method was vegetable oil, and pickling and canning also worked quite well, whereas the control and sugar solution didn't work quite as well, and pineapple juice was actually the worst of the solutions. And so for canning worked particularly well because you actually boil the jar before putting the produce in, which kills any pre-existing bacteria. And then when you put in the produce and seal the jar, that works by cutting off any oxygen from reaching the produce. And as you can see, after 14 days, it was just a bit of browning, so it worked out quite well.
Next was pickling, and so this actually worked decently thanks to boiling also killed off any bacteria currently on the food. Submerging it prevented oxygen from getting to the surface for the most part, and the vinegar solution, which also was keeping away the oxygen, was doing a pretty good job of killing off any bacteria, as its low pH was creating a pretty hostile environment for the bacteria to survive in. Our results, as you can see on the top one, the banana kind of turned brown, and the apple looks decent. It's a little bit hard to see just because of the color of the solution, but we think that the banana ended up turning more brown just because it had more of that polyphenol oxidase enzyme that we're talking about that causes browning. But for the most part, the pickling did a pretty good job of preventing any real decomposition.
For vegetable oil, it works quite well because it creates a strong barrier around the produce. So it works really well for preserving cooked produce. However, with raw fruits and vegetables, it actually creates bacteria growth, which has been linked to food poisoning and rare disease botulism. So based on our results, the fruits look really well because there's no mold, no browning, no dryness. However, it makes it unedible, so it is not a good solution.
So for sugar, with further research, we found that sugar does actually attract microorganisms when it's exposed to air and water. You can think of like adding sugar and water for yeast to like make bread rise as a microorganism, as an example. So what we found with this also is that sugaring is best when used in a heavy solution, meaning that it would be saturated or completely oversaturated. And we didn't actually even make a simple syrup, which would be a 1-to-1 ratio. We actually did that 2-to-1. So we found that for the fresh produce, it only caused browning, and it did attract some kind of microorganism because that decomposition was present. Yeah.
And then finally, pineapple juice. So the reason pineapple juice works in preserving fruit short term is because of the presence of citric acid, preventing the oxidation of other compounds. And you'll see I provided the structure of citric acid below, and we know that each vertice represents a carbon that binds with hydrogen. And so it's these hydrogen that are seeking electrons and preventing other compounds from being oxidized. And so therefore our results showed that after 3 days, there was very minimal browning, which means that the pineapple juice was what was reacting with oxygen rather than the fruit. However, after 6 and then 14 days, mold began to grow and the fruit began to go brown, which means that that pineapple juice had reacted with the oxygen and now it was the fruit that was turning brown. And you can kind of see in the pictures above that layer of mold forming and browning beginning to happen, but it's a little difficult because pineapple juice is yellow and murky. And then our conclusion was for this one that it's good for short-term preservation, but should not be used any longer than 3 to 4 days.
So in conclusion, we found that our hypothesis was disproven. Remember, again, I said that it was that acidic solution, but we also found that pineapple juice was actually the worst method. It's more important with the exposure to O2 gas for deciding which procedure would be the best. So in that, we did decide it would be vegetable oil as that non-aqueous solution. However, as mentioned, it can be prone to food poisoning, and it's also a lipid structure and very high triglycerides. So even if used on a big scale for solving something like world hunger, which is what our goal was, as said in the beginning with the UN goal, it would ultimately render the food inedible or completely alter its health benefits.
And then we just have our works cited.
Thank you.
Look at these. Leave it like a. So I will see you when you get back.
Okay.
We'll get you all queued up here. Need one moment to queue up. All right. There we go. Let me get this guy going for you guys. Sorry, we're just transitioning between project presentations. What is up here? Okay. Fabulous. I think we're all good.
All right, hi, my name's Matt,
I'm Bradley.
I'm Abigail.
and this is our sustainability project, and we chose to address water shortage. So just to give some initial background on the problem, every day 11% of the world's population doesn't have access to clean water. So in an effort to achieve the 6th UN goal from the 17 goals of sustainable development, which is to ensure that everybody has access to clean, sanitized water, our group decided to run experiments on possible ways to passively collect water. And we did this through a biomimicry approach. And biomimicry is the idea that we can look to natural processes or mechanisms and copy them to achieve a similar result. So like how water beads off the surface of a leaf and falls to the roots to be collected, we propose that we can coat a material with a coating to have water repel off and then to be collected. Now, approximately 550 gallons of rainwater can be collected per 1,000 square foot of land per 1 inch of rain. And this is important because what we're aiming to do is to increase that surface area by applying this coating to the walls of buildings or just unsealed driveways and increase that surface area so we can increase the amount of rainwater we can collect.
So basically what we were testing was whether or not these commercial sprays were effective at preventing the water from getting into the wood. So what we did was we coated the wood with these sprays, and then we were testing to figure out whether or not the wood was able to absorb that water or whether it was not able to.
All right, so essentially our procedure, you can read it, but it was, we take 6 blocks of wood, coat 4 of them, 2 with one spray, 2 with another spray, and then put them in this dome that regulates humidity. So you set it to 93% humidity, and then see how much water is collected at the end to see how much, like we weigh the blocks before and then weigh them after, see how much water they absorbed and how much was let off. Okay, this is our results, although we can't really pay much attention to them because we think the scale was broken when we did it because they weighed less afterwards, which doesn't make any sense because some water would have inevitably made it inside the wood. So, like, what are you going to do? But those are our results. I'll go next slide. Our procedure that we would do next time to update kind of, and obviously we would use a better scale, but also we would use a more sustainable coating for the wood, maybe like beeswax. We looked a little bit into that. That's a hydrophobic thing, and it's fairly cheap as well. Use a different material. We used wood because we figured that is something that you would see a lot, like in structures and houses, stuff like that, buildings. But a different material might be more helpful in our experiment. And then change the shape of the wood. We would want to make it like a dome shape so that the water rolls off of it easier instead of just a block.
All right, so some of the science behind the project is that water is a polar molecule, which means that it has positive and negative sides. Wood is made up of primarily two compounds. One is lignin, which is the one on this side, and the other one is various carbohydrates. Those are both polar molecules, which means that when they react to water, the water is absorbed into the wood, which is a good thing when you're talking about a tree that's trying to grow in a forest. But when it comes to buildings and structures, waterlogged wood is not the best. It's not the best material, and it doesn't have the greatest longevity in other words. The coatings were silicone-based coatings that were made, and silicone is a non-polar molecule, which means that it doesn't attract to the water. So by covering the wood with a non-polar surface, the water was not able to infiltrate the wood, and the water was then able to be collected, or would have been able to be collected by some other collection source.
So after completing our experiment, we came to two main conclusions. The first one was that we needed to run our lab a little bit longer. And due to lab constraints, we only were able to run each trial for 15 minutes, which doesn't accurately simulate the effects of rainfall, which would happen over multiple hours. And the second one is that we shouldn't have chosen wood as our material. And we initially chose wood because we designed our experiment keeping in mind that in developing areas, wood is the primary material that these structures are made out of, and wood is actually it's a sustainable material if we harvest it the correct way. So that's why we chose wood, but wood was definitely not the right choice because it's actually hygroscopic, which means that it has the natural tendency to absorb water within its pores. So when we put it in the humidifier, it actually absorbs some of the water and messed up our trials and how much water we could actually collect off of it. But our procedure still applies to whatever material we would need to coat in the future and try to collect water off of. And our project goal was to find a way to ensure that we could have clean water for everyone in the world. And we tested that on a small scale, but we could scale this project up to cover entire buildings. And this would have two main purposes. One, it would be able to passively collect water through the hydrophobicness of the coatings we're using. It would actually increase the structural stability of whatever structure we're coating, because we can prevent a majority of the water that gets into the wood. We're preventing it from rotting early and extending its lifespan. One overarching question we had within our experiment the entire time is, would the water that we collect actually be able to be drinkable in real world conditions? And we found that technically, yes, we could drink this water, but as we pollute our planet more and more, this water collects the pollutants that are in the air and can actually become acidic. And you wouldn't really want to drink that, but it would be a perfect candidate to replace the fresh water that we use for agriculture or personal use, which would then put less stress on our water systems and increase the amount of water that we have available to everybody for drinking and anything else you need water for, which achieves our UN safety goal. Thank you. Any questions?
Righty. We've got one more for you today. And here we go. Or would you, you know what, you might prefer. Yeah, I just hope it comes out correctly. That's always the fun part. Come on. I'll move that for the moment so people can see your name, but afterwards you can just move the taskbar out of the way.
Oh, yeah.
I still want to watch it.
So my name is John.
I'm Rachel.
I'm Kendra.
All right, so in our experiment, we looked at a number of different paper products, and our goal was to determine which paper product is best for the environment. So the question we want to answer is, what is the easiest paper product to dissolve? So some background information, paper production leads to a lot of environmental issues, including air pollution, water pollution, agricultural waste, and greenhouse gas emissions. It also accounts for 25% of landfills, and that's in large part due to our poor recycling practices. However, we can't eliminate paper altogether because it's a big source of income and it's a big need in our daily lives, especially in times like COVID. You can see the demand for paper has gone way up. And so, as I said before, our goal is to determine which paper product is best for the environment, and in doing so, which will have the lowest carbon footprint.
So in our experiment, we had the following materials. So we had one sheet of toilet paper, paper towels, tissue paper, and a wet wipe. And we also had to have access to tap water, just normal tap water, 4 clear cups for each material, and a spoon for stirring our materials. And this is our procedure. We first started out with weighing each sheet of the paper product and making sure that each sheet, the mass was like their dry mass. So we had to make sure that the wet wipe was dried out first before measuring its initial mass. And then we found the mass using an analytical balance. We then filled each of the 4 clear cups with just tap water from the sink. And we had to make sure that the volume of the water used was roughly the same, just in case if that changed anything. And next, we tore each of the sheet into smaller pieces, either using hands or scissors. And we're making sure that none of these sheets got missing, or else that would have changed our mass measurements. Then we submerged each of the sheets into their respective cups. Prior, we were labeling each cup with whatever material was going to be in them. And then after 20 minutes, we let them, we were stirring them for those 20 minutes. And then afterwards, we let them sit on like a little shelf for about a week. And we were stirring them at constant time intervals. And then after that week was over, we poured out the water, making sure, again, none of the paper products left the cups. We let them dry out, and then we took pictures showing the change in the physical breaking up of the paper products.
Okay, so our next few slides are going to show pictures throughout our experiment. So this is the beginning of our experiment. We cut up the paper products and we're getting ready to put them into the water. And then this is right after we submerge them in the water. And then this is about a week in after having them in the water. We stir them up numerous times with a spoon to kind of simulate agitation and a toilet flushing. And then this is right after we drained them and they're still wet. And then this is them dried out at the end of our experiment.
So these are the experiment results. So as you can see on the left side, these are the mass before for all the paper products, and then on right, it's the mass after. So that's after drying, after submerging them in the water, and then after drying when the experiment was done. So we took these results and we made a graph of the paper product masses before and after the experiment. So as you can see, the light blue is the mass before and the dark blue is after. So looking at this graph, you can clearly see that toilet paper had the greatest decrease in mass. Meanwhile, the wet wipes stayed exactly the same, had the same mass before and the same mass after. So further going into these calculations, we found the percent dissociation. So we took the mass after, divided it by the mass before, then multiplied it by 100%. So this percentage is how much paper product is still left. So as we can see, the toilet paper in bold, that had the lowest percentage, which means it had the lowest mass after and the most dissolved from our experiment. And then we can see the wet wipes had 100%, which means that it had the same mass before and after, so it did not dissolve at all for our experiment. So the reason for this, the toilet paper makeup, so it's made from virgin tree pulp, water, bleach, along with other chemicals to extract the fibers. So the tree pulp is made of cellulose, C6H10O5. So that's the first part of our chemical formula. Then we have calcium carbonate, CiCO3, and it's added to build strength for the cellulose fibers to cling to. So that's why the toilet paper stays together, because of this calcium carbonate. And then toilet paper is also processed with chlorine bleach or sodium hypochlorite, NaClO. And then we have water. It's involved in the makeup of toilet paper, but we added it at the end because the toilet paper is being submerged in water. So taking this information, on the next slide, the chemical equation is just at the top. So we're taking each of these molecules separately, and we know that each one is polar. And polarity means that they do have a full or partial charge areas to form hydrogen bonds with the water molecule that's attached at the end. And since we know that H2O is a polar molecule as well, and like dissolves like, we know that the toilet paper will dissolve in water. So for the other paper products, tissue is also made from tree pulp, but it's also infused with chemical binders to help retain the shape similarly to toilet paper. And it has wet strength to prevent it from disintegrating when you blow your nose. Paper towel, in a similar manner, it's made from tree pulp as well, but there are 2 layers that are bonded with light harmless glue. Toilet paper ranges, so it can be 1 ply, which is like this one right here. This is the one that we use. It only has 1 paper, 1 layer, but the ones like the Bounty ones, they do have 2 layers that are glued together. But all the paper towel is supposed to have small pockets of air to help trap the water when you absorb it. That's the use of paper towels. And then for the wet wipes, they're made from non-woven fabrics, fibers such as cotton and rayon, and then plastic resins like polyester, polyethylene, and polypropylene. So the flaws with these products, these other 3, such as tissue, paper towel, and wet wipes, they do not dissolve as readily as toilet paper because they are infused with chemicals like polyester to help keep them from breaking apart when applying the force. So with tissues, you are supposed to blow your nose. So anything that comes out, you do not want the tissue to break. For paper towel, its main objective is to absorb liquid. Like I said before, that's why they have the pockets of air. So they shouldn't as easily as toilet paper because we're trying to soak up liquid. And then for the wet wipes, their main purpose is to clean surfaces. So while you're cleaning surfaces, they should not be easily broken down. But toilet paper, on the other hand, it's supposed to break down.
So for our conclusion, by our analysis, we believe that the non-perpetual stirring, lack of other environmental factors such as bacteria that you can be found in like the toilets or furthermore in the sewage, and our short time run span, which was only a week, may have caused for this very small decrease in mass before and after. And so we assume, especially with the toilet paper specifically, if we had allowed a much longer runtime for an experiment, as well as having other chemicals and factors involved, we would have a much more demonstrated change in mass. And we believe that this mass change, especially for the toilet paper, would have decreased roughly 1/4 of its original mass. And yeah, you can go on. These conditions, this assumption, was assumed because of a previous experiment by a different group of people who conducted a similar experiment in Tasmania. So these people, Brittle and Kirkpatrick, were comparing paper products such as tampons, toilet paper, and tissues in terrestrial environments. So what they were doing was they were burying the paper products at different levels in the ground, such as like 6 feet to around 15 feet underground. And the paper products they were comparing were toilet paper, which was treated with bleach, and then just regular toilet paper, the tampons, and the tissues. And their results showed that the toilet paper and the tissues had decayed more readily than the tampons. The unbleached toilet paper had decayed much much more than the bleached toilet paper, and the tissues had decayed much less so than either bleached or unbleached toilet paper. So this chart demonstrates their results. So as you can see, throughout the 6, 12, and 24 months, the toilet paper had shown the most amount of degree of decay. As you can see, at the 24 months, it was around 4 degrees of decay, and the tampons had the least amount of change in their mass.
So our conclusion of our experiment, we know that toilet paper is engineered to dissolve in water because its purpose is to be flushed down the toilet. So it does not get stuck in the pipes or the septic system because it can easily be dissolved. So this should be the only paper product that we flush down the toilet because it is the only one that is engineered to do so. And we know that this is the most environmentally friendly paper product because of the degree of decay. The other paper products that we compared it to, they do cause greater harm to the environment because they do not decay as much. So if they are put in the sewer systems, they can clog all the pipes and the septic system, and then also marine life. So if it gets into any oceans, then it does not decay as much, and it can cause harm to marine animals. And since their ability to break down as quickly as toilet paper, therefore they should not be flushed down the toilet. And then finally, for our UN goal, our sustainability goal was to ensure stable consumption and production pattern. So this, we kind of went more towards the production pattern of paper products. So we know that the world uses natural resources very unsustainably. And from 2010 to 2017, the increase in the global material footprint increased from 73.2 billion tons to 85.9 billion tons. So that was just over 7 years. So that's a great increase. And for our production pattern, we are designing a solution that is to create more paper products similar to toilet paper because we know it is the most environmentally friendly and it dissolves the most. So these are the sources we used, and we hope you enjoyed.
You guys can go ahead and sit down. Thank you very much for everybody who came out for today. We're doing this one more time on Wednesday. And I will have a recording of anybody who would like to take a look at it. You can certainly be in contact with me and I can send that along to you. Thank you very, very much and have a wonderful day.
Thank you.